Washington State University. Go Cougs!
Okay, so now I want to go on to a related topic which is on reduction. So here reduction is basically, it's an operation, it's a technique really, as a way to aggregate results coming from multiple threads. Okay, so I will use the example of the sum code here. Okay, here sum here is, let's say I give you n numbers to add, okay, and I give you p threads, right? How do you efficiently parallelize that adding of those n numbers? Okay, that's the problem that we are interested in answering, but for that we have to understand what we'll do if you have a single thread, right? So all we'll do is take the first variable, add it to the second, take the answer, add it to the third, fourth, like that, right? This is our pseudocode. When you write a simple for loop, this is what it does. It walks through the input from left to right and then adds the numbers by keeping a cumulative sum and reports the answer at the end, right? How many operations did I perform? To add n numbers, I performed n minus 1 additions. That's the work that my serial code did, right? Now let's see how to parallelize it. So let's say I have n numbers, let's assume we have n processors, okay? So which means each processor can get one number, right? So can I not use the same construct? Thread number 0 works on element number 0, thread number 1 works on element number 1, thread number 0 passes its data to thread number 1, thread number 1 adds, takes the result, propagates it to thread number 2 and then 3 and then 4, code is parallel, we are done, isn't it? No. Why? Exactly, it's in fact worse than serial, right? Because if you should look at the from the point of view of the last process, last thread. The last thread which is looking at the nth element has to wait until all the first n minus 1 threads complete, and then only it gets a job to do. Until then it's sitting and waiting, idle, right? So we have taken the n minus 1 work, and in fact we have added threads, and the management overhead also will be there, and that's why I said worse, right? So the runtime will be worse than the serial execution. So that's not clearly the way to parallelize it, okay? So however you can do is generate partial sums, like one of the ideas that were generated, right? You can say, oh, I have a total of n big array, it's an array of numbers, n numbers. I can divide that up into n over p chunks, where each thread gets n over p chunks, and then internally those threads independently calculate those partial sums. Now I have a total of p threads, which means I have a total of p partial sums, right? Then I have to somehow aggregate it, right? So the main idea there is n over p is what each thread will be working on locally, and that's independent. My local sum will be different from your local sum. You and I don't have to talk, at least as of now, until we finish, right? So that's the approach that we'll take whenever we do. So essentially what we'll do is we'll take a big long n array, chop it into pieces of equal sizes in this case, and then generate a partial sum. Let's say that partial sum is what is indicated in this slide. It says x1 is the partial sum generated by thread 1, x2 is the partial sum generated by thread 2, using whatever block or batch of array that it looked at, okay? Then we can use essentially this reduction technique. Reduction techniques is very simple once you see this. So what this says is basically thread T1 sends its data to thread T2, right? At the same time T3 sends its data to T4, at the same time T5 sends its data to T6, right? When I say send, I mean really it's saying do this, it's probing it or prompting it. And what the thread T2 is doing is it's adding up x1 and x2. T4, because it now knows it needs to add these two numbers, it does that, right? So this is happening in one parallel step. Now starting from 8 partial sums, we are down to 4 partial sums. You repeat the process. Now here T2 passes its value to T4 so that those values can be added. At the same time, T6 passes its value to T8 and those values get added. This is the next parallel step. Now we have reduced a problem of size 4 to a problem of size 2. Then we do one more time, we are done. Right? So instead of 8 means that there are 7 steps, 7 additions that needs to perform left to right if you think serially. In parallel, this means 3 parallel steps. In a more generic sense, if I have a total of p partial sums, to add them up I will use only log p to the base 2 parallel steps. Log of p is much smaller than p, correct? And the reason why we call this reduction is because of this. We reduce a problem of size 8 in the next step to 4, 4 becomes 2, 2 becomes 1. That's log, that's the definition of log. You take n, keep halving it, how many times do you have to halve it to get the answer 1? That's log of a value to the base 2, correct? So this is reduction, and this means that the threads need to act in synchronous fashion here. They need to coordinate in a very nice manner, right? Every thread needs to know which other thread it needs to pass its data to, right? So there are ways to, if you are sitting in a parallel programming class, you will be writing code for this to implement this reduction. There are nice ways to do this, okay? But in this 2-hour workshop, actually OpenMP saves us because all this is done in a single line, okay, single primitive. So it's what's called the reduction operator. I'll show you the code, okay? So out here, let's open the sum computation serial again, or compute serial, yeah. So here, okay, so this is the sum compute. Go to the line of code that says this function, compute sum. Line 106 or 104, okay? So my for loop is there. This is what I want to parallelize. So I want to identify what is it that I'm trying to reduce. The output variable coming out of the sum is this variable called sum, right? So that's what I want to reduce to. So I want to just tell the OpenMP system, help me reduce this. So what I do is, we'll have to insert the OpenMP pragma. So I think, did we modify this? Yeah, we have openmp.h, and then I go to line whatever. So I go down to the compute sum, okay. Say pragma OMP parallel, and this is a for, right? And here, let's look at the scoping first. What all variables are used? Well, variable I is used, and because variable I is the loop iterator, OpenMP recognizes that. So you don't want to define scope for I, because I will be taken care of by the OpenMP environment, okay? Because it takes different values of I and gives it to different threads, yeah.
So OpenMP is recognizing that when you're coding in C. So if you're trying to use OpenMP in Python or R or something, you still have to call it Y for your for loop, or will it recognize it's in the for loop?
No, you will have to have this for loop if that's what your question is.
But I mean, the fact that it's called I, is that specific?
Oh, no, not at all. You can call it whatever you want. Yeah, you can call your loop variable anything you want. It will recognize that loop variable. It's the loop variable, okay? So pragma OMP parallel for, and here A is an array, right? It's a variable that's being used, but it's an array. So I have to say A needs to be shared, right? Because it's visible for the all the threads. They need to be accessing the same array. But it's good because it's doing it in read-only mode. It's not changing the values of that, yeah.
So I thought that by default it was automatically
It's you are right. Just as a good coding practice, you need to be doing actually the right coding practice is this. You say default none first. You force yourself to say I want to define the scope for every variable that I'm going to be using inside this. Then the compiler will not compile until you do that. So it's the more very careful way of doing it. Yeah. Okay. So shared, but now I is taken care by the OpenMP parallel for, sum is another shared variable, right? Now if I say sum here, we have a problem. because sum is being written on to by all the threads at the same time, so we are looking at data corruption. We don't want to do that, right? So what we'll do, instead we want to reduce on sum, so we'll say reduction, I think it's, yeah, and then sum, we say this is the variable that I want to be reducing on, colon, and the operator, oh no, actually it's the other way around, sorry. So I'm saying sum is a variable that I want to reduce using the operator, the binary associative operator plus. So what you're doing internally is you're doing adding numbers, right? You can also multiply, and we can use exactly the same technique of reduction that we discussed. So replace all the pluses by multiplication, it will still work, right? Or you can use other operators like, you know, XOR and stuff like that. The requirement is they need to be binary associative. Binary means it needs two operands. A plus B equals C, it means plus operator uses two operands to create the output, that's binary. However, associative means A plus B plus C is same as A plus B plus C, which is fine, right? So essentially the order in which you add these three numbers doesn't matter, you get the same answer at the end. That's important for this reduction to work. If you take subtraction, for example, that won't work. A minus B minus C is different from A minus B minus C, could be different. Same for division. So binary associative operators, matrix multiplication is a binary associative operator. You can multiply matrices in that order as long as you keep the relative ordering, you know, you basically multiply different parts of your products, you will still get the same answer, okay, things like that. So you basically specifying what is the operator here that you're using, and then you're specifying sum, and internally the OpenMP environment is taking care of all this log P business. We don't have to worry about it, okay. So once we have done this, let's see if this code compiles. Sum comp and minus of OpenMP. Okay, so now that it has compiled, let's run it. We'll just say the array size maybe million, and let's give it one thread. Here I'm getting about 6 milliseconds, right? So 2 threads 3 milliseconds, 4 threads 1.5 milliseconds, so it seems to be scaling, right? So you double the number of threads, you are halving the runtime. It won't obviously keep happening due to Amdahl's law, right? Make sense? So this is reduction. So whenever you want to add things and stuff like that, binary, as long as the operator is binary associative, you can use reduction.